There you go. We are now online on YouTube.
Okay, cool.
Now on stage is yours.
Okay. Yeah, yeah. Thank you.
I'll present you.
Yeah,
So
go ahead.
it's our pleasure to have Antoine Rozel from Enstitüsü. Antoine is,
Doesn't work anyway.
he finished his PhD in Lyon in France, and with Yannick Ricard, and he did his postdocs in UCLA,
USC, yeah, USC.
University of Second Choice. University of Portugal. They say Portugal. So, and that's how I met him in Roma while he was doing the perspective modeling with Claudio Cacciana. He then moved to ETH Zurich, working with his group with Paul Tackley. You would know the name in terms of producing very interesting results on mental convection. Currently, he works on planetary scale global mental convection models, which he'd like to further understand how the habitable crust on the Earth is formed throughout 4.3 billion years timescale evolution. And he also works in grain size in the plate tectonics. So he does very large scale stuff rather than regional tectonics. Does very large scale stuff.
But he does compute.
He does compute mostly.
Yeah, we compute things. Yeah, yeah.
That's what counts.
For you, it does.
He's not what I'm told.
You're glad your friend
He's
Gerald
not
is
what I'm
not
told.
here.
Other job.
Yeah, no. You're glad your friend Gerald is not here.
Yeah.
So in some ways, yeah, there's lots to see from Laurent's work. They publish in Nature Science every year, and maybe a couple of them. So that's important to mention. So his work has a lot of implications. Yeah, thanks again for coming, Antoine, and welcome.
Well, thank you for inviting. Thank you so much. So I had an email from Oz last evening saying, "Oh, make it simple. There's going to be geology," which I found hilarious because I always think geologists deal with much more complexity than we do. So I will try to anyway. Well, actually, I stopped showing equations in my talks long ago, so principles, there's no problem. All right. So, well, first, before I start, I want to, I really want to thank my colleagues. So, can I see the arrow? Yes. Yeah. So Diogo Lorenz was a PhD student in our group. Lots of this stuff comes from him, and he's now in UC Davis as a postdoc. CJ Charitra Jain was also worked a lot on implementing felsic cross production in the code. I'm going to show lots of his results. He's now a postdoc in Durham University, actually. Gregor Golabek, you may have heard of him, is doing a lot of geochemistry and global geodynamics, also a lot applied on Mars and other planets. So I work a lot with him. Taras Garia and Paul Tackley are professors in our group in ETH, and Patrick Sanan is really the applied mathematician in our group, so he really helps a lot as well. So none of this work could have been done without these people. All right, so yeah, I really like to talk about all the planets of solar system. I work also a lot on exoplanets actually, but I don't want to present it here because there's very few data. So I'm just going to go through solar system objects quickly. Actually, how long do I have for the talk? Actually? Yeah.
It's 4 hours.
4 hours. Okay, perfect. And then I'm going to present a bit what thermal convection is and what I think are the limitations of pure thermal convection. Then a bit of thermal compositional convection with crust formation, and then some implications. Okay, so right, so you probably have seen this already, but basically we have not so many planets to look at in the solar system. From a geodynamic perspective, it's really a very small sample. So yeah, Mercury and Mars are the small size. The Moon, Io, is very interesting as well. I put Iapetus here because never really mentioned. This is a little satellite of Saturn, I think. That is actually a rocky body and almost spherical, with some actually it's interesting object, I think, and very few people study it, so I just point at it sometimes. I actually didn't study it explicitly yet, but it's part of the plans. And of course, Venus and the Earth are the big rocky planets in the solar system. Okay, so a very quick overview. Mercury is actually believed to be in the stagnant lead regime. So you can see it's a very old surface full of craters with some, well, the elevation, but there doesn't seem to be any tectonic unit really there. There is some big faults due to the contraction. You know, planets cool down, then they tend to contract a little bit, and this generates stresses in the lithosphere. So this is what sometimes you can see. But other important feature is the core is really large compared to the planet itself. So Mercury is a very dense planet. So, and you can see on these colors here, there are some, so this is the false color, of course, but there are some chemical anomalies in the crust. So the crust, it's not like it's one type of rock with homogeneous composition. It's actually a little more complicated than this. Right now, I switch right away to Venus. So Venus is like the twin sister of the Earth from the size point of view, but it looks very different. So this is only the topography, so you cannot see much on Venus because of the clouds. So that's actually a big limitation. So this is radar image. You can see the elevation quite well. You can see also the reflectance. Some people know a lot more than me about this, but basically this is the kind of image we have. So one very noticeable feature is the crater distribution is very homogeneous on Venus, and Venus is very young. So the surface is about, well, this is, you can argue, but between, let's say, 300 million years and 1 billion year old, homogeneously everywhere. So if you count the craters, it's not like Mercury where it looks like it's 4.4 billion year old or something like that. This is a young surface, and it's homogeneously young, which is very puzzling. Venus is the size of the Earth, so, you know, it's not trivial at all. Why? Very, well, okay, the image is a little contracted, so these are spheres, but yeah, so there are people have been working a lot on this radar image of Venus. And in particular, you can find these review papers from Ivanov and Head and lots of co-workers, I believe, who basically what they did is looking at every little quadrant on Venus and actually trying to do a structural map. So this is a structural map, global scale of Venus. You probably know more than me what all these formations mean, but basically they are volcanic provinces, they are rifts, they are what they call tessera, so which is compressed material and deformed material. There are lots of different units that we can observe. So there is some data on Venus. Then if we go back on the global map, so you can see that there's this big, there's several types of, the topography. So this is very gradual topography. High, you can see you have a gradient, smooth gradient. So it looks like a dynamic signal, like a plume would be pushing from below, when it would uplift everywhere, but it doesn't necessarily require a lot of crust. This might not be a crustal anomaly here, but if you look up there, then it looks more abrupt, like there is a step. So it could be that there is also crustal steps, basically. So there are different kinds of topography features you can see. Oh, it was before, I think, 11 kilometers, yeah. Sorry. Right, so there are noticeable features. Yes, the surface is young homogeneously, but it seems like still there are some anomalies clearly on Venus. So I say that loud because in geodynamics community, people say, well, Venus is stagnant. So there's no deformation, it's just stagnantly, like Mercury. But more and more, lots of people seem to really disagree with that. So here, I just want to show what data is. So if you zoom at the north, you have this, sorry, I can show again, this is this region here, particularly high region. It seems like this thing here actually is indenting to the north. So I don't see that, but people like Lyra Harris and Jean Bédard see that. So they show that this thing looks like an indenter, and then so this you can see in the radar image. You can see that there seems to be like like the Himalaya. Basically, they do an analogy with the Himalaya. So basically, yes, the surface is homogeneously young, but it seems like there might be tectonic activity right now. So they don't hesitate to do stuff like these drawings where you actually have, so that's the Lakshmi Planum on top. You actually have an upwelling here and rifting, and then the rift, so I'm losing the mouse all the time. Rift here is pushing this way, and then you have a block here, and then it indents, and then you have some big mountain chain. Some people would kill me for saying that. Like, people are very dogmatic about Venus is in the stagnant lead, and what are you talking about, and blah, blah, blah. gravity doesn't show that, or there's also gravity data. So this is completely ongoing, discussion. For me, as global geodynamicist, I think it's very interesting to look at. So I just want to point out what people did. So Bedar and Harris don't hesitate to even, based also on gravity data, to even produce models like this for Venus, where you have so this would be the plateau that is indenting. This would be the mountain chain, basically, that looks like Himalaya. And to do that in a kind of stagnantly planet, you need some anomaly below that mechanically can actually push. So what they say is there is mantle wind. So this, I think everyone agrees with that. Even if it's stagnantly planet, you have convection below lithosphere. And what they say is that, okay, if you have something that looks like a craton, then this thing will be pushed by a mantle wind and generate deformation, and could explain this mountain chain in the north of Venus. Okay, yeah. Well, I don't really need to think. It's more people counting craters would say hundreds of millions of years. Yeah. From models, I could reproduce anything by changing the viscosity. So what the age they give is interesting for me. Yeah. I think it's about 500 million years. All right. So now, if we move to the Earth, so you would. Magnetic field, yeah. Sure. Yeah, it is. Oh, yeah, absolutely. I cannot cover everything. Yeah. Yeah. So if we move to the Earth, so I'm not going to teach you anything about the Earth, but basically, one very important thing for global geodynamicists is that there are cratons. There's oceanic crust, continental crust, and there are cratons. And so these black contours here are globally strong things. And this is something that no one can generate in a global geodynamic model. It never happened. You have people, you can pre-impose cratons and then deal with them, but no model for the moment can actually create these things. If you want to study the Earth from 4.5 billion years ago, magma ocean stage to present day, no model for now generate cratons. And for me, it's a challenge for the next. So yeah, I just want to point out, we know that it is here. So clearly, yes. So you can, it's no question. Obviously, there are these big objects, and they didn't deform very much in the last hundreds of millions of years. So if you go back on Venus, Venus is the same size than the Earth. So you could question, are there cratons on Venus? Actually, I don't know, but it's possible. People mentioned this already. So there are some noticeable features, as I said. So this is my poor hand drawing. Yeah, I don't believe this, but I just want to point an idea. There might be some cratons on Venus. So Harris and Bedar already point out that this could be have a keel, and then this is pushed by mantle flow. And then there could be other provinces. So if you look at the global structural maps of Venus, you could say, oh, this could be cratonic, region. Below there could be some very strong unit. So I'm just saying, this is for me an interesting question. Okay, and then if we move to Mars, Mars, so it's a relatively small planet with a very noticeable feature, which is the crustal dichotomy. So I'm doing just a list of things we need to reproduce as geodynamicists to be confident that our models, seem correct. So clearly, this is topography of Mars. So the north hemisphere is quite low, and the southern hemisphere is much thicker. So the crust is much thicker. You can see overimposed the magnetic anomaly here, actually. But that's not really the main point right now. And there's also volcanic activity that has been still going on for recent on geodynamic timescale, geological timescale. So most of this crust at the south is 4 billion years old, and little bit of it has been overimposed more recently, hundreds of millions of years. So that's actually still a challenge in geodynamics. If you take normal models with just viscosity that depends on temperature and you run it, you will never create something like that. So this requires already a little more advanced model. Something that is noticeable, I think, is like this Tharsis region. Is that Tharsis? Yeah, I think so. Yeah, Tharsis region, where you have still volcanism that's been going on kind of recently. So, and there's lots of opening here, so it kind of looks like expansion. Yeah, so this is also something that I think is quite mysterious, because again, people will say, well, Mars is in the stagnant lead regime, so there should be no deformation on Mars, in the geodynamic community. So, you know, there's more, it's like Venus, there's more to do than just saying, oh, it's stagnant. I think there's quite a lot more to do. Okay, so Io is quite interesting object as well. So satellite of Jupiter. So it's really small, but it's lots of volcanism on Io, lots of sulfur volcanism. Actually, there's really amazing images, in case you didn't see that already, but there's really amazing images of it. And there's clearly ongoing volcanism, as you can see, where the eruption actually is so big that it's even in the spherical geometry. So it's really incredible volcanic activity. So I don't say much more. So yeah, this is due to tidal forces around Jupiter and the other satellite. So the mantle is being heated because of tidal forces. So yeah, if you want to reproduce, for example, a heat flux on Io, we need to, well, we can input some heat from inside. That's no problem. But then we need to have a crust model. We need to form crust, and then we need to look at the temperature profile to try to reproduce some potential data. Right, and then the moon, obviously you can see chemical anomalies, which is creep anomaly. So there are lots of maps. So the moon is very well studied, of course. So there's chemical compositional anomalies a bit everywhere in the moon, and particularly that's iron, and you can see also thorium. There's this one noticeable feature, really big, which is called the creep region with a K. So this is also something, and it's only on one side. So it's also something, some compositional feature that is noticeable and should be a target of any geodynamic model which want to reproduce data really precisely. Okay, so I did an overview of all planets, what we have on a very simple level. Now, what do convection models actually do? So usually, if you take, well, so I didn't show the equations, it doesn't matter. But basically, you know, what's warm just goes up because it's light. If you take a rock and you warm it up, it becomes lighter. It just wants to go up because it's in a gravity field. That's it. So, okay, so then you know that the viscosity, well, experimentally, you know, take different temperatures of rock with different temperatures and deform it, and they see if it's warmer, it deforms more easily. So the viscosity depends on temperature. Cold stuff doesn't deform easily. So if you do that, you get naturally in a code, you just take a convection code and you say viscosity depends on temperature, you get a stagnant lid right away, always. If you strong, if the viscosity depends on temperature enough, you will get very easily stagnant lid. So if we would do that, then you will always get stagnant lid planets. So you will always get some kind of Mercury, basically. If you say, well, okay, I know that rocks can also break, so I'm going to use a critical stress, a yield stress. You say, okay, if the viscosity, if the stress exceeds the critical value, I'm going to decrease the viscosity. So I'm going to say it breaks. If you do that, you get something that looks like mobile lid. So geodynamics, where I'm very careful not to call this plate tectonics. Plate tectonics is full of complexity. Here we talk about mobile lids, but actually it kind of looks the same from a very general point of view. So if you say viscosity depends on temperature and I have a yield stress that is low enough, I do mobile lid regime. And in the boundary between these two things, these two convection regimes, we have the episodic regime, which basically what happens is, well, the lithosphere grows. Because it grows, it becomes heavier. Well, the whole load increases with time, and then the stress is increased. And at some point, it's so strong that it reaches the yielding. And then the lithosphere, as you can see here, well, here first, starts to break. So you have a rift forming, and you have a downwelling forming. I don't call this subduction. People would kill me. You know, it breaks. So then it entrains the whole lithosphere, and then convection actually can even stop for a moment because you have a lot of cold material. They're huge, like 300 kilometer, 500 kilometer lithosphere at the core mantle boundary, can stop plumes for a moment. And then the lithosphere grows again, etc. So this is episodic because the lithosphere grows, then delaminates, then, well, subducts, grows again. Okay, so that could look like Venus. Great. solve Venus, no problem. Because, well, then if you do that, the lithosphere here is homogeneously younger. So that was actually quite successful, and that's probably part of the reason why Venus has a young lithosphere. But then you don't explain like the Lakshmi Planum thing, the indentation and stuff like that. So you can already explain some first order things. And a lot of people in geodynamics believe that this is enough. This is it. We have stagnated planets, we have plate tectonics, and we have episodic regime. End of the story. So before I move to thermocompositional convection, I can show just one quick result that we had. There was actually a bachelor student who ran some models, and we wrote a paper. She was quite some work, but basically what the person was Rico Naff, Swiss bachelor student. What he discovered is you can have this one ridge in some convection models. You can have stagnant lead and one ridge appearing, opening slowly, but no subduction zone forming. So actually, this was not really reported so much before, and people don't seem to know much about it. So we did observe that this can occur. So I have a little movie. Yeah. So these are what convection models look like. So on top left, you have temperature field. You can see the rift at the south, and then it jumps to the north. And you have big downwellings, but it's still stagnant lead. Yeah. So I just want to show that this is possible, at least in models, which is not so common actually. And it's still just thermal convection. See the viscosity field, strain rate, velocity, stresses. You can look at all the fields, of course. But basically, yeah, that's a little paper we had 4 years ago now. So it's possible to form a ridge in a lithosphere that looks stagnant. And actually, that could apply to Mars. Southeast region seems to be extension, and there's no subduction on Mars, clearly. Simple convection models, yeah. It's thermal convection, super simple. Actually, we're quite surprised about it. Okay, so now I want to talk about limitations of thermal convection. So these two models are exactly the same conditions. So on the left, the viscosity depends a lot on temperature. On the right, it depends a little less on temperature. It's the same model, same initial conditions, but the rheology is a little different. The activation energy of the viscosity is a little different. That's what is it. If you look at the temperature, if you look at the temperature scale, you have jumps in the mantle temperature by 1,000 Kelvin. If you tell that to a geologist, he will tell you, or a geochemist will tell you, well, come on, 1,000 Kelvin for the Earth, it's completely impossible. The Earth decreased its mantle temperature by about 300 Kelvin in 4 billion years, maybe maximum 400 Kelvin. So clearly these models, they are very nonlinear and they are not realistic. So we have to be careful with pure thermal convection. So yeah, you can see the end result. Like this one is, I don't know, 1400 Kelvin. It's really cold. And the other one gets quite warm. So we need something, we need to buffer this. And yeah, so now I move to thermal compositional convection. So first idea, this is the temperature, this is the average mantle temperature versus time. This is, the blue one is if you have no melting, so you have just thermal convection, and that's temperature. You can see it's probably a stagnant lead model. It just increases, and then reaches some value, and then some equilibrium occurs. Depends on the boundary condition. Doesn't matter. If you have melting, this just never happens. You can warm up for like 100 Kelvin maximum, and then melting happens. So then the temperature cannot increase more, because if you reach the solidus temperature, rocks start to melt, and this actually absorbs heat. Well, actually, it's at constant temperature, but then when the melt goes as a crust to the surface, then you actually lose some heat. So melting and crust production right away has a first order effect on the planet evolution. It just buffers the mantle temperature. And that's extremely important in geodynamics, because then, you really have a way to make everything look more stable. You cannot get to completely crazy states. So this is the first thing that is extremely important for geodynamics community. Okay, so how do we do melting crust production? So I didn't show any equation or anything, but I can explain basically how this occurs. So this is, now I'm talking about stag YY, which is the convection code we use in ETH with Paul Tackley. It's one of the main global convection codes. There are other convection codes, but for the moment, none of the others can produce crust if they are global scale, planetary evolution. There are some local models where crust can be produced. There are lots of codes. Actually, it's great because we can benchmark our stuff. But on a global scale, for the moment, it's the only code. So the way to do it was many ways to do it, but what we do is to say, okay, we're going to predefine a density profile. So that's the density of two compositions. So we live now in a world where there's two types of rocks, very simple. But it's more than one. We have basalt, mold, and we have Hausbergite, so enriched and depleted. That's, as complicated as it gets. So one very important feature is that if you look at basalt, so this is depth here and density. So if you increase depth, density increases. Well, because pressure, it's compressible convection, and you have jumps. So because you have phase transition. So a very important one is that, well, first observation, basalt is usually denser, almost everywhere. So that's important. And second observation, there is a phase transition in the lithosphere. Around 40, 60 kilometer, basalt turns into eclogite and increases density like crazy. So if you form a basalt in a convection code and you have this phase transition, the lithosphere will always be suddenly super dense if you generate enough basalt. That's very important. I'm going to present why this is very important here. So, but from our point of view, we have pre-computed density profiles. And then if we have like rocks of a different type, we look at this density profile and we know it's density. Okay, so now I'm going to talk about volcanism and plutonism. So I want you to know what this means for geodynamicists. So, okay, this grid is like the numerical domain. So, each of these cells have a temperature, composition, some whatever we want to define. And in these cells, there are little dots called traces or markers that are just moved in the flow. Okay, so there's a bunch of equations for that. It doesn't matter at all. But basically, what is interesting for us is that part of these traces will know that there is a melt because we compare the temperature of the cell to the solidus temperature. If the cell is overheated, we know we should produce melt. So what we do is producing melt. So we know, oh, okay, these orange traces, they are molten. Actually, there is a little residue behind, usually quite big residue of Hausbergite mainly. And these molten traces, we say, well, they should produce crust. So we're going to say, well, let's move down everything else. And then these guys, they're going to be erupted. So we're going to cool them down because when they see the surface, they radiate their heat to the atmosphere. And then we reintroduce these traces in the code. So that's eruptive magmatism in our code. That's as rough as it gets. We could solve for two-phase flow, fancy things, but it would take forever. Actually, it is in the code, but we just cannot use it. It would take a month to solve for 100 million years. It's impossible. We are interested in billion years evolution. So volcanism is treated like this. And then we get some geotherm that is quite cold, basically, because we put some cold material and we add back down all the rest. Okay, plutonism, intrusive magmatism is the same idea. You take the melt, you detect the pre-existing crust, and you track down everything that is below it. So you know there's already basaltic crust up there, this blue stuff. And then the melt, you just re-intrude it below the crust. So, and this is really difficult to do numerically, actually. This was years of coding. So Paul Takle did that. And we, with Charitra Jain, we upgraded this for felsic crust formation. But so for the moment, that's what we get. And then you get another geotherm that is much steeper because you intrude basalt, molten basalt. But then what we didn't do, we didn't cool it down. It stays below in the lithosphere, so it doesn't see the atmosphere. So this intruder is still warm. So for us, it's just, okay, we're moving particles in a grid. And then when it melts, we transport these traces. That's what we call magmatism. Okay, so sorry, this is really ugly sketch, but right. So basically, what's important now is that, okay, we have a lithosphere, we have a geotherm. And, if we have basalt in the lithosphere, if it goes deep enough, it turns into eclogite, as I already said, with a density profile. So we just teleport mass, we pile basalt on top of it. If it reaches this eclogite position, it becomes dense. All right, so now which kind of convection regimes can we get with that? Well, actually, we can get similar things, but now we can see the composition in the mantle, in our nice 2D world, basalt, hasbergite, very simple. So, yeah, we still have mobile lid. So if you have mobile lid, you have quite large anomalies in the mantle. So you can see red is basalt, blue is hasbergite. So you can see stuff being subducted and then mixed, and then you still see anomalies in the mantle, which is probably happening on Earth right now. There is some compositional anomalies right now. So for seismologists who interpret mostly things in terms of temperature, and a lot of people work on water now and actually composition. So this is actually interesting for them as well, because you can see, oh yeah, of course we produce, compositional anomalies. The interest of this code is that we can do it self-consistently. We don't need to force it or to input something. It just happens because we melt, produce crust, and then subduct it. For the episodic regime, you can see that, well, it's so sudden, it's so strong, and you have the whole lithosphere resurfacing and going at the CMB. Then you can see around the core there is a lot of basalt, well, or eclogite. Yeah. So the composition, the distribution of composition in the mantle depends strongly on the convection regime. And we still have the same convection regimes with crust production. At least the 3 that were observed before are still observed, and we have other ones that I'm going to show. And then you also have the stagnant case, where basically you have, well, very thick crust and depleted mantle below it, and the rest of the mantle is still quite depleted. So this could mean that Mars, for example, or Mercury, is probably quite depleted because it has a lot of crust. Okay, then, great, so what do we do with that? So one important message, so this is now the work of Diogo Lorenz, who was a PhD student with us. So the idea is very simple. What he says is, if you create crust, you are going to break the lithosphere much more easily than if you just do thermal convection. So, if you take, so this is viscosity of the mantle and y-axis, and that's the yield stress, the critical stress. So, okay, if you take the top view, if you take the top plot, this is just normal thermal convection. If you have a low yield stress, if rocks are easy to break, then you're always in the mobile lid regime. If you increase a bit the yield stress, you have some kind of episodic resurfacing. Actually, it's more like at the beginning of the evolution, you have resurfacing and then it becomes stagnant. And if you have a large yield stress, you are always stagnant. So this is the global normal picture. If you switch on melting crust production, the mobile region is much larger. So you can have mobile lid for a larger yield stress because you create crust, you create density anomalies. Eclogite is heavy, so it breaks more easily and you get more mobility. And interestingly, the episodic regime is much larger in the parameter range, which is really cool for Venus, because what people were saying before basically is, okay, you can have episodic resurfacing, but only in a very small range of yield stress, right? It's like very unlikely that Venus exists basically if you have only thermal convection. In this case, yeah, interesting. I can talk about this. That's because the convection regime depends a lot on what happens. Actually, there's several. It's very patchy, right? We were very upset about this. Actually, it is correct. So actually it's a more difficult message, but basically it might very well be that it's very chaotic, and sometimes if plumes gather in the lower mantle, then they generate massive plume, and they can do a resurfacing. And sometimes it happens, sometimes it doesn't. So we could rerun this model with a slightly different noise in temperature, and it's not going to happen. So actually, the best to do would be to run all these models 100 times with slightly different noise, and we would have a distribution of these things, of different regimes. Yeah. But so because we were upset about this, we did this envelope here, which is analytical prediction of the critical stress. So this one equation in my talk actually is basically predicting the maximum yield stress after which we should be in stagnantly. So the blue curve here is the analytical prediction, and we are close to the actual result of the model. So this is the critical yield stress predicted. And we have an extra term here that I derived looking at the thickness of the eclogite crust. Basically, it's an extra load. You put this extra load and you get a different stress. So we predict that if we create crust, we break the lithosphere much more easily.
You move the lithosphere much easier.
Sorry?
You mobilize, you move the lithosphere like a
Yeah.
plate tectonic type region.
Well, here it's more episodic, actually. It's not, well, yeah, it's also this region is a little larger, yeah, but it's going to become more episodic. Yeah. Okay, so, yeah, new convection regimes. Okay, so this was with eruptive magmatism, actually. And since then, Paul also coded the intrusive magmatism. Okay, so to make it simple, basically, now we look at the extrusion rate. So, okay, I didn't mention that, but when we run our code, we can specify, do I want to erupt all the magma, or do I want to intrude it, or do I want 50-50, or, I can partition eruption and intrusion. But it's not self-consistent. It's just a choice at the beginning, which is it's not satisfying. But for the moment, it's what we have. So here we say extrusion rate. So if we are on top of this graph, we are erupting everything. If we're at the bottom, we are intruding everything. And here is the yield stress in the x-axis. And what we are seeing is mobility, so the mobility of the surface. So the blue region, mobility equals 0, is stagnant. Here we are mobile, again, so it's same message. But if you look down here, actually, if you intrude most of the magma, then actually you never reach stagnant lead regime. So whatever yield stress, you are going to deform. And this was quite a curious observation. So we tried to scratch our head very strongly. And we came up with this interstitial plateness. Okay, so basically, what happens is we intrude a lot of magma. And what happens is plates are forming because you have a lot of intrusion sites are very deformable. So you can deform the lithosphere, but not too much. It's not generating a global resurfacing, but it's moving a little bit. And then, yeah, so because we intrude so much, we keep the lithosphere deformable. It deforms a little bit, but not dramatically, not like in the mobile lead regime. So we try to come up with some. Sorry, I'm going to show this first. This is what it looks like. It's completely unreadable, but it actually happens. So because of that, we did a little cartoon that is readable, I hope. And so this is what schematically happens. I can show you the model again afterwards. So basically, this is the crust. This is enriched mantle, and the white stuff is depleted mantle. It's depleted. The lithosphere are actually not represented here. It could be the crust as well. It can be depleted asthenospheric. Yeah. No, it's very important actually. That's very different. But yeah, probably part of it is the lithosphere. So okay, if you intrude something here, you're deforming the lithosphere and you're making some kind of rift. And you're also intruding in some other sites that generate lots of eclogite. So this stuff wants to go down, and it's warm, so it's deformable. So it actually goes down. So doing this, it forms a little microplate, And when it pulls, so we see coherent velocity. It pulls this microplate, but then something else happens because the mantle is still quite warm. So then you have another intrusion, and you create a new kind of plate boundary. And then the velocity vector is longer. So you have a bigger plate, and then something else happens. You have delamination of some eclogite somewhere. Then you have a new intrusion site, and then you form a new microplate. And this is all happening in like 5 million years. So we have like little plates appearing, kind of shaking a little bit, and then new intrusion sites and stuff like that. So we observe this. So I first was saying, okay, this is ridiculous. It's way too low resolution. What is that, But Taras Garia came in the office and said, whoa, I observed this in my model. It's perfect. So it was like, okay, maybe it's actually, so Taras runs local models with much higher resolution, and he observed exactly the same thing. So still, the big limitation of this is that we are doing this in 2D, and clearly this looks like in 3D, an intrusion would not be like a linear thing, it would be a plume maybe. So I'm not sure if this is real, but we observe this at least in 2D. We unfortunately cannot run the simulations in 3D. It does not converge. So it's another problem, but basically it's not stable enough. We are working hard on this. But so these models you can see or not, you can see a little bit. That's the white arrows here are the surface velocity, and the background behind is velocity. So you can see that, you know, this stuff is orange and then blue, then it's yellow, and then there's the blue region here, which is another kind of microplate. So it looks quite low resolution here, but basically we did observe this systematically. So we need to do more on this, but what we are observing that intrusive magmatism seems to be able to generate some kind of little microplates, you know, and that could be applicable on Venus, because it's exactly like Lakshmi Planum. You have this stuff that is shaking a little bit, but it cannot be mobile completely because craters would show it. So it could actually fit, you know, something like Venus. And we call that plutonic squishy lid. After lots of meetings, we didn't come up with anything better. I'm so sorry. But PSL, yes, okay. And then, yes, so other results. So this was also Diogo Lorenz. What? I didn't write his name. Okay, sorry, I forgot. Strange. So this was Diogo Lorenz, who was I was mentioning already, who did also the previous study with Paul and me. And this is a Nature Geoscience paper in 2018, last year. So here we are comparing eruptive versus intrusive magmatism. So on the right, you erupt everything. On the left, you intrude most of the magma. So what happens if you take one planet and you just change this? So I already talked about the plutonic squishy lid thing. And now here we show that there's more than that. There's actually, if you intrude everything, you have these microplates forming, and you refertilize the mantle a lot. So actually you get enriched mantle. So this we were expecting, but what we were not expecting is the intruder actually, the models with intruder actually cool down the mantle better. If you intrude, you cool down the mantle better. For two reasons. First, if you intrude, you increase the heat flux. So the heat flow out of the planet is large by diffusion because the lithosphere is thinner, and this is good at cooling. And second, if you refertilize the mantle, if you recycle basalt, then you can melt more easily because enriched mantle melts more easily. So if you refertilize, you can melt more, and then you kind of, it's self-sustaining, nice erupting planet. Sorry, well, intruding planet, but volcanic. So basically, if you intrude, you diffuse heat to the atmosphere better, and you can melt more and intrude more. So actually, the downwellings are cold. It still looks like a stagnant lid planet from the global perspective. There is no plate tectonics going on or resurfacing, but it's refertilizing a lot and cooling better. If you erupt everything, you form a very cold lithosphere and crust. You know, so, and the crust, you know, is cold, so it doesn't actually recycle very much. So you get a very depleted mantle, and because it's depleted, it cannot erupt or it cannot melt anymore, so it warms up. It's completely counterintuitive. We thought, okay, if we erupt the heat, we're going to cool down better, right? But actually, no, because of some thermocompositional feedback, the eruptor stays cold, and the planet doesn't cool down very well. So yeah, the model is shown below. So the composition field is here. So this is enriched, and here it's completely depleted, and the lithosphere is full of basalt and eclogite. Okay, so now I talked about formation of basaltic crust in the code and what happens, you know, to the convection regime if you form basalt and eclogite. Now we thought, okay, what if we generate continental crust? That would be really great if we could generate that. So first thing, we talked a lot to Taras Garia, who has experience in this because he does it locally. So he said basically we could take, well, there's many ways we can do that, obviously. But one big review paper on TTG formation was by Jean-François Moyen, 2011, where he showed, okay, if you have temperature and pressure, if you look at all the TTGs, so this is the felsic material you find mainly at the Archean, some granitoid, yeah. So this is what probably has been transformed to continental crust in present day. Sorry, I should stop on the beginning. So yeah, of course, if we want to form continents, we're not going to form continents like from mantle to present day, at the present day from mantle to continental crust. There are several stages. So the idea here is that you take enriched mantle, you generate a molten basalt, you erupt it, you have solid basalt, then you somehow re-subduct solid basalt. If it's hydrated, it's going to turn into some granitoid, which is called TTG. And this TTG later will be remolten or metamorphosed, or something will happen, and it's going to become continental crust right now. So for us, who have only a Hasbogite basalt world, the next challenge was to take basalt and transform it into TTG. So this occurs only in 3 temperature and pressure regions, following the classification of Jean-François Moyen. So basically, I parameterize these windows, and I say, well, let's run a model and form basalt. And we track water as just a particle advected, which is very wrong, but this is the first thing we can do. And then we look at the temperature, the geotherm, you know. So I told you geotherm depends a lot if you erupt or intrude. If you erupt everything, it's very cold, so you're going to have a cold geotherm. If you intrude everything, you're going to have a warm geotherm. So it's very important for this kind of things, because if you want to turn a hydrated basalt to a TTG, you need to be in the good temperature and pressure region. Okay, so that's the idea. So this is what it looks like. This is the most successful model we have. So temperature on the left, TTG source, which is, so you can see almost nothing. TTGs are only formed close to the surface. So you see some dark dots appearing sometimes. Basalt field on the right, viscosity, melt fraction, and water. You can see water is very warm, but you know, that's what we have. So basically, I can play it again. First, the core was very warm and generate large plumes, and you see a lot of little, you know, blobs of basalt going down, you know, like really large scale. This is planet scale. So imagine a 300-kilometer block of basalt being created suddenly and just sinking in the mantle. That's the first billion year of evolution of the solid mantle. Well, it's just a model, but that's what we see. So yeah, I'm just gonna, I think it's very important that I show that, so I play it again. So yeah, huge plumes, and then the core cools in the models. This is a billion year. Yeah, sorry, I should have put a time. Yeah, so you have stagnant episodes, sometimes doesn't happen much, and then you have sudden kind of resurfacing a bit everywhere in the planet, and then it can suddenly burst, and here is a global resurfacing occurring again, and then it becomes stagnant again. So lots of things can happen. It's very chaotic, and you know that's why the convection regime sometimes, you know, is episodic, sometimes just stagnant. It all depends on what happens in the deep mantle, and it's very chaotic. Okay, so that's what it looks like. So the main result of this study was to say, okay, the amount of TTG that we should produce if we have only a simulation with Hasbogite basalt, we can see if we are in the good pressure temperature to form TTG. In this study, we did not form TTGs. We only looked if we should have formed it. And the result is very simple. If you intrude everything, you can form TTGs. If you erupt everything, you can form only the high pressure TTG. So we just show simple. If you erupt everything, there's no way you're going to form low and medium pressure TTGs, which is the big 3 families of TTGs observed in the field. So these 3 envelopes show the volume of TTG that should be produced for the given intrusion efficiency. So if you intrude nothing, if you erupt everything, you cannot form all TTGs observed in the field. And if we go around 70% of intrusion, 30% of eruption, which is actually consistent with what is observed in the field, then we can understand that, yes, there are 3 types of TTGs, and we can form them in simulation. So, yes. Yes. Yeah, we have a master student coming next month for trying to code the whole thing. It's going to take a while. But yeah, so to do this better, we need many things. Well, the eruption and intrusion efficiency depends on the viscosity of the melt, so we need to parameterize that. And the viscosity profile of the lithosphere, probably. If it's very stiff, there's no way it's going to intrude so well, so it should erupt more. If it's a bit deformable, then the magma should stop and intrude, and probably more than that. But yeah, we want to do this very shortly, yes. That's a big limitation of our model. Yeah, then it could depend laterally, you know, in some places it should erupt, in some other places it should intrude. Yeah, we are doing only simple things here. Okay, so a little sketch, very simple. If you erupt everything, so that represents the lithosphere. Melt pockets, eruption, cold. So this is geotherm. Too cold. The windows for TTG formations are not found by the system. Geotherm is too low. So if you erupt everything, it's too cold. If you intrude everything, you delaminate the whole lithosphere, and you keep only a crust. And then you can see the low pressure, medium pressure TTG windows, but the high pressure is hard to get, doesn't work. And if you do a bit of both, which is what is observed in the field, when we confirm, we see the same in our model. So happy, seems to work. Okay, and now Charitra Jain, who was PhD student in our group, came, and his task was to actually form felsic material. So now, okay, we see we need to intrude most of the basalt. Now let's form continental crust. And we spent 4 years coding this, and now it works. So I proudly present it. So what now happens is, you remember I showed you the little movie where you had particles taken out, and then you take down the lithosphere, and then you reintrude it. So now we do this, but with 2 layers. We have, you can see the TTG crust that is already here, potentially, and basaltic crust that is also already here, and you have melting events. So that's the mantle here. So every cell has now traces of different compositions, like before, but now it's also TTG. There's also pure basalt. Before it was already a basalt-Hasburgite continuum. Now we distinguish families of compositions in every cell, and all these traces have a different melting temperature, which was not the case before. So now we distinguish this in families, and latent heat removal and all these nonlinear processes. Yes. So we did it in a very bad way up to now, and now we have a really good way to do it, actually. I don't present it, but basically this is what I'm doing right now. We have composition-dependent saturation of water, and also partitions solid and in the melt, and we propagate upward if it's saturated.
Water-wise, the system is not conservative, right? You're losing water. You're using all tiles to the atmosphere.
Yeah, we track outgassing and ingassing. Yeah, absolutely. Yeah. So now what we do here is, okay, if we melt the mantle, then you can produce a basaltic melt or a TTG melt if you are in the good pressure and temperature conditions. And then this TTG melt will be erupted or intruded in the TTG crust. Then the basaltic melt will be erupted and intruded in the basaltic crust. So we have several melt compositions, and they are teleported in several places radially or vertically. But now this is now in the code. So yeah, and this was really a nightmare. I thought it would be like super easy. Oh yeah, well, basalt melts and produces TTG, easy. No, actually it's really a problem, because the thermodynamics of this one cell is actually much more complicated than before, because we have a very nonlinear system and new types of equations to solve. Yeah, it was quite tricky. Okay, so this is preliminary results in review. So this would be very early stage. So you take a homogeneous mantle, and you just run the simulation. So yeah, this is I didn't zoom in this slide just to show the global picture. So that's temperature here and composition. So now we have TTG, basalt, Hasburgite, and the melt. And we have a TTG basalt mix that also appears sometimes. Okay, so what happens is, first the mantle was this color here, the mixed mantle, this kind of dark green. And then you can see that this is warm. So the initial mantle is quite warm, which I think everybody agrees with. Then it forms plumes, which pulse and propagate laterally. So by default, if we do nothing, we have plumes pulsing up and squishing material laterally. And then, so this forms layers, so I can zoom to the next. This is the same thing, primordial material, plumes pushing laterally. White is molten Hasburgite. It's so warm that we actually melt, well, it's partially molten, but we do melt a bit of Hasburgite. And then, so the dark purple is basalt, eclogite. So we form layers of basalt and eclogite that are being intruded and stacked like below each other, like this. And then doing this, the head of the plumes spreading laterally actually form molten basalt which transform into TTG, and then the TTG is squished to the whatever is between two plumes, and then we form some aggregates of basalt and TTG material like this. And lots of TTG is actually entrained in a mantle in these simulations. So we do believe that from these models that it might be that there's a lot of felsic material that has been entrained in the mantle at this time. It's what we observe. And then at a later stage, so this is like 3 billion years ago, still have very large density composition anomalies in the mantle, and thick basaltic crust and some continents being formed. Well, we call these continents, but this is TTG provinces that should be transformed into more complex material that we see now, but we cannot compute it yet. For the moment, we already formed TTG, and we're very happy about it. It was really difficult. So now we have this kind of amount of material, and this is the crustal volume at the surface. Oh, low battery. Do we have electricity? Because this is not working, and it says low battery, so it might shut down.
You talk too much, that's why.
Sorry. So I keep talking.
No.
It's plugged, but it doesn't work. Right, so we can see here that this is the amount of crust being formed in total. And so we form a lot of crust right away. So the green and blue curves are typical crust formation models by geologists, field people who, you know, think, okay, we take the rock distribution, the distribution of the ages, and we see several pulses. There's lots of models, but they typically come up with this kind of curve. Some of them are actually wiggle a little bit more, but you know, and then our model behind, so different colors correspond to different eruption and intrusion efficiency, but we are able to form exactly the good amount of felsic material now after 4 years of coding, and we're really happy that it's actually working. So we don't know if the convection regimes, if everything is realistic, but at least we are able to form now continents. Still doesn't work, so it might shut down. Let's hurry up. Okay, so I have a final drawing that I just want to show to summarize what we think based on models. Actually, since I'm out of battery, I'm going to make it quicker. Let me just skip to the last version of it. No, come back. Yeah, right. So this represents the evolution of the Earth from 4 billion years ago all the way up to present day. So this is time. This here is the mantle cut from inside. Basically, you can see what happened. So this represents what we see in our models. I'm not saying this represents the Earth. So, okay, so in our models, we have a warm core, okay? So we have to do that because we conserve heat, and if we don't have warm core, the core at present day is too cold. So I don't know if this is correct. This is actually a big limitation, but we start from a warm core. And because we start from warm core, we have big plumes. And big plumes generate a lot of deformation, which seems to fit what people observe on the field. Well, so I don't want to detail much of the field, but people see a lot of deformation in the Archean. So for us, it makes sense from plume point of view. Then in reality, so this is not in our models actually. In reality, there are cratons being formed, and we do not form them yet. I'm working on this a lot. A lot of people are working on this. We did not make it happen yet. This is big limitations of geodynamics. Even if we create crust and continental crust now, we still don't have cratons. Then plate tectonic stacks at some age, maybe it started progressively in different places, I don't know. But then plate tectonics started. And then cratons are still here, and then the material that was entrained has been remixed mostly. Okay, so very conclusion, basically we have cratons on Earth and piles. Could very well be that there's also cratons on Venus because it's a similar planet. It's different from surface point of view, but it is the same size. So that's a natural question, I think, to address. And then, right, to conclude, basically, thermal convection cannot explain everything for planetary evolution. You can explain present day Earth quite well, but the evolution of planets is probably requiring melting and cross production. Eruption versus intrusion is very important. You don't have the same result at all if you erupt everything or intrude everything. It's really important. We even see new convection regimes thanks to cross production. So it's not just, you know, changing a little bit of geotherm. It's actually doing lots of nonlinear things. If we intrude enough, we can get continental crust if we code the whole thing, but it's possible and it's important. If you code magmatism, you really should code intrusive magmatism as well. Otherwise, it's going to be hard to be realistic. And then, yeah, we are looking into cratons and other planets and thinking that this could be a very important challenge in the future. Thank you so much for your attention. Sorry, I hope I didn't speak too long.
Start from the student.
Yeah, thank you. I'm a young student here. Yeah, I was wondering what's happening at the outer core mental interface. I mean, you keep track of things there, and there's a heat flow term still that we keep there. And is that, I mean, do you have any idea about the outer core dynamics that can affect the mantle?
Yes, so there's several core models in the code. Usually we use, for the Earth, we use Buffet, I think is the name. So basically, it's just thermal evolution. We have a heat capacity for the core, and the only thing that can happen is heat flux at the outer boundary. So we look at the heat flux from the mantle and say that this is equal to the heat flux inside the outer core. And then we cool the core. And if it cools enough, the one other thing is that you can create the inner core because there's latent heat for that. So if you want the evolution of the core, you need to also create this to take into account the growth of the inner core. So we have, yeah, we consider the core adiabatic. It's adiabatic. It's so vigorous, yeah. We neglect viscous dissipation and things in the core. We only have heat flux and heat conservation, yeah. So we have actually it's quite fancy core model, but it does neglect sometimes.
Can the mantle convection drive any kind of convection in the outer core?
Yes, yeah, sure, but we do not resolve the convection itself, but we just say, yes, there is convection in the core, so the core loses heat, and we compute its heat. Yeah. So this is all self-consistent.
That's relevant for the magnetic field and dynamo theory and
yes.
stuff like that. Right?
Absolutely, yeah. Yes. Well, if there would be parameterization of dynamo for heat fluxes, then we could use it. But there's no such thing because we're still fighting to know what's actually generating dynamo. There's at least 4 processes able to generate dynamo. So we do record, yeah, the boundary conditions, the inner core site, and heat fluxes. We can use it, but for the moment we don't do anything more. Yes. Mm-hmm. Yeah. No idea. So what happens is, so this only occurs when you have a depth-dependent yield stress, but no homogeneous yield stress. So usually, you say you have friction, you have brittle part, you have a viscous part in your yield stress. If you do just that, you don't break the lithosphere. So we add another yield stress, which is the one I was coding in your version this morning. So you need to yield the lithosphere from inside very strongly. And this is not physical. We don't know why, but we have to do this. We know that the lithosphere breaks. So yeah, if you remove this term and you have only a depth-dependent term, you can also yield the lithosphere if you go for very low friction. So what we did is to go to intermediate friction, which makes the base of the lithosphere quite strong, but the middle and top of the lithosphere are quite weak. If you do that, you can get rifting, but subduction zones can't form because it's very strong. But we're not in a horribly unrealistic range. We're actually in quite reasonable range. And since we don't really know what yields the lithosphere on Earth right now, then it's still a reasonable model.
But you don't necessarily call that subduction.
There is no subduction in these models. There are downwellings, but the lithosphere is not untrained. That's what I mean. Yeah, you don't, you have thermals. It's like small scale subduction. Yeah, sure. No, we produce this, but in these models with ridge only, it looks more like stagnant with one rift. Yeah. Yeah. Mm. Yes. Mm-hmm. Oh yeah.
Geometrical data available, which can help us by projecting the structure. There, I think we have only chance to constrain your flow models or your models in general based on who sent you electric data.
Mm-hmm.
I'm just a comment, of course, if you don't have anything, you don't have anything to do with but I have also second, you don't answer maybe, but I have also second question to this question. In general, we know from the Earth model, again, based on geometrical,
Mm-hmm.
there's not only one type of carbon behavior in our planet because that is simply North China carbon is completely different than what can be a couple of
Mm-hmm.
so then that's also another issue. So
Yeah.
we may not have one single model to
Yeah.
decide on.
Yeah. Well, so what I'm looking for right now, so I didn't present this, but right now what I'm looking for is grain size evolution. So I have lots of models with grain size evolution as well. And one thing that could help forming cratons in general is to, it looks like suddenly the mantle can become much more viscous. That could be due to grain growth. So the idea would be, okay, a very depleted mantle that was only formed at the Archean could have a very strong grain growth because the Hasbergite is extremely depleted. And this term could freeze whatever is here. And then lots of geodynamical scenario can occur. And what would happen in general is, it would freeze anyway. And then you could have cratons formed by like compression or some other processes, plumes, and yeah, exactly. Lots of things can occur. And then whatever would occur, it could freeze. And then most of it would be destroyed later. Some of it, especially in 3D, could still remain, because in 2D you tend to remix everything nicely. In 3D you could easily avoid some pieces, then you would get cratons right now. I actually don't know. We just try to make it happen. We have some tests where it happens, but then I don't know yet about distribution of composition and mixing the cratons. Super interesting problem. Mm-hmm. Yep. Oh yeah. Mm-hmm. Yeah. So just quick comment on your first question. There is quite some data also to reproduce for us the gravity crust composition